Be here. This is our board week. We have board meetings today, tomorrow, tonight. It's absolutely exhausting, and Walter couldn't be here. And if he were here, I know he would tell you a number of things. One, just how important and significant this book is. I think all of you probably know Walter before he became Steve Jobs' biographer, of course, was an Einstein biographer. And the book is important not just as an extraordinarily illuminating book about Albert Einstein, and not just as an extremely important book about the history of science, but rather a very important book about 20th century intellectual history, about the history of ideas. He probably would also tell you, and Doug may mention this as well in the lecture, that the Aspen Institute had a little bit something to do with this book and with provoking or triggering, seeding some ideas that led to this book. But he isn't here, and so it's my pleasure, which has additional meaning to me, because Doug has been a friend of mine for more decades than we'd like to admit. And I wish I could say I had some influence in this book. I had absolutely none. But I can say that I'm not surprised at the book and its significance, because I have known Doug as someone who has really a remarkably broad and deep intelligence across not just, as you would expect, the natural sciences, but the humanities and the social sciences as well. Indeed, we were students essentially in parallel, studying social sciences and philosophy, which were Doug's fields before he turned with great passion and skill to physics. I, however, didn't have the skill to turn to physics. I might have had the passion, but I wouldn't have had the skill. So I remained more true to social sciences and humanities. But I think it's the kind of prism through which Doug sees the world as a scientist and as a humanist that makes the book so fascinating. So even though I am a very weak substitute, it is a great personal pleasure for me to be here. And it is now my pleasure to bring up Ramamurthy Shankar from Yale University, who will do the true introduction to this evening. Thank you very much.
Good evening. I'd like to start by making a few announcements about future events at the Aspen Center for Physics. On August 14th, there is going to be a dialogue called The Maps Inside Your Head by Vijay Balasubramanian from University of Pennsylvania. And as you know, a dialogue is a different format from a lecture. You can interrupt the speaker, you can ask questions, and it's more free-flowing. So I think you would enjoy that a lot, especially the topic is about maps in the brain, and Vijay is a person who really is both a particle physicist and also very involved in neuroscience. The other event is August 28th, when there is going to be a movie called Particle Fever. It's about the discovery of the Higgs boson, and it'll be at the Wheeler Opera House, and dessert and reception will follow. All right, so now I'll tell you about Doug Stone, and normally, introducing somebody requires a lot of work, finding enough material. In my case, it's really one of embarrassment of riches, because I've known Doug for 40 years now, and we met at the time that was just mentioned when he was switching from social science to physics and at Harvard, and I was teaching a summer course on quantum mechanics. And the class had only 4 students, and it's supposed to last about 1 hour a day, and thanks to Doug's limitless interruptions, it was about 3 to 4 hours a day, followed by more talk at dinner time in my apartment. And the reason was that he would not accept anything for granted. And obviously, I liked what he was doing in the class because I wanted those classes to last that long. And I was also planning to write a book on the subject. I wanted some young person in his state of development to see if everything I said was crystal clear, both to him and to me. So when I finally wrote the book, I had a big acknowledgement to Doug for helping me sharpen my own thinking. That's very relevant because quantum mechanics is what is going to be the topic today. Anyway, after those summer courses, Doug went to Oxford shortly as a Rhodes Scholar, and he made his complete transition to physics. And I went to Yale, and then a few years later, Doug ended up as my colleague at Yale. And Yale was very eager to get him because he had done this very impressive piece of work on what's called mesoscopic systems, where he noticed some funny business and in his usual way would not brush it aside, but dug deeper and hit gold and discovered what's called universal conductance fluctuations, one of the best things he's known for. And finally, I will skip the remaining years and come to his writing of this book, in which he shows the same tenacity to get to the bottom of things. And he does not, I'm grateful that he does not repeat the usual nonsense about God not playing with dice, because that one sentence attempt to summarize Einstein is such a disservice to what he did. It gives the impression, number one, that he didn't understand quantum mechanics. That was the case of sour grapes. And he had nothing to do with his discovery. In fact, it's quite the opposite. He had everything to do with the birth of quantum mechanics. He embraced the ideas of quantum mechanics much more vigorously than some of the proponents like Max Planck. He saw the role of quantum mechanics not only in the one discovery Planck made, but in atomic physics and solid-state physics. Then he first person to talk about probabilistic distribution, a probabilistic description of physics. He worked on he discovered the Bose-Einstein condensation. Then he later in his life pointed out the rather bizarre things about quantum mechanics. And they're all very true. It's just that we become more accustomed to them. So even though as a practicing physicist, I knew that Einstein had done all these things, I'd never put them together and realized how significantly he had affected the development of quantum mechanics. So I look forward greatly to hear Doug recount that tale, and I'm envious of all of you who have not heard him before. Doug.
Okay, thanks, Elliot, for that very warm introduction. And Shankar really is my oldest friend in physics and also my greatest mentor in physics. And he is the quantum guru who helped me get to where I am today, both as a researcher and probably also in having a perspective on that allowed me to write this book. So it's very nice to have that introduction from him. Now, it's not an easy thing to say something new about Albert Einstein. I will concede that this gentleman has gotten some recognition for his contributions. But if you talk about, as I do here, a new perspective, maybe I can illustrate that from by means of a famous cartoon from the New Yorker. Maybe you've seen this. This is the Manhattan view of the world from 9th Avenue, where things get pretty muddy pretty quickly, far away. And as a practicing physicist, even somebody interested in history, our view of Einstein's contribution to atomic theory, to quantum theory, was sort of like this. Okay, so there was relativity, which was at the center of Manhattan. And then, quantum was good. It was still in Manhattan, but it was almost in the river. And then, the public, since they don't have the training in quantum, if they know about it, it's out there in China somewhere. So they have this distorted perspective, and through some happenstance that I'm going to tell you about, this is what I think the correct view is. So there's a huge quantum sign in Times Square in recognition of Einstein, and relativity is really good too, but it's just a little further out in my estimation. So that's the perspective I'm going to bring, and I'm going to try to tried to document in this book, which is for general readers, but also for practicing scientists. And the way I came to write it is actually an Aspen story that I'm going to tell you about. There was a hint of that in Elliot's introduction. I'll only be able to tell you a few dramatic episodes because it's a long book, and this is, we're going to keep this lecture within a reasonable compass, as they say. And then I'm going to reflect briefly on the nature of Einstein's genius, which I got to have a feeling for by reading 2,000 pages of his letters and so on. And then the big question, why, as Shankar has already alluded to, did he reject what you could call his greatest creation? Now, the way I got into this was through something very different, my own research. This is a PhD student of mine, now a professor at Princeton, Hakan Turici, and he was completing his thesis on a rather recondite subject called quantum chaos theory, and he was having difficulty writing the introduction to frame the problem. And I remembered that there was this obscure, believe it or not, paper by Albert Einstein that related to this. So I said, well, let's see if Einstein can solve our problem. And it was a joke, right? I didn't really, but I got the paper. It was fantastic. It was so fantastic that I wrote a sort of exegesis of the paper for Physics Today. And it came out in 2005, but I did this in 2004. And that was it. So all I knew, I wasn't an Einstein scholar, all I knew was this little corner of Einstein's work. But other people didn't know I only knew that. And it was, looming was the World Year of Physics in 2005. And actually the Institute and Walter Isaacson had decided to steal a march and to have their symposium early so they could be the first one. And they decided that in 3 days of discussing Einstein's significance, they really should have an hour or two of science. So they broke up his work into cosmology and elementary particles and quantum, and they asked me to do the quantum bit, the 20 minutes of sort of summarizing this huge book that I eventually wrote, not huge, big book. So I got a crack at it, but the main thing that happened was I immediately realized this was too technical and it wasn't the most famous things, the most important things he did, so I should learn about the more important things. And when I learned about them, I started to see the tip of this iceberg that that really Einstein was the person that understood these things, and not so much Planck, not so much Bohr, not so much even Heisenberg and Schrödinger in a certain way. So that was the motivation to write the book, well, sorry, it's not quite the motivation. So I started to see the tip of the iceberg, and then a year later, I was invited to this lecture, to do the Pagels lecture in the World Year, and sort of expand on what I had learned. And so here's the front page of my talk in 7th of July, 2005, where I was just talking about the first episode in my book between Einstein and Planck. Okay, and after this lecture, which was well received, several people came up and they said, "Where can I buy your book?" And I kind of chuckled because I'm pretty busy. I have a big research group and I'm chairman of my department. And I thought, well, this is a pretty important story. Maybe I really could write a book if you give me enough time. So I was very much encouraged in this idea by Walter Isaacson. So he immediately said to me, well, you need to get an agent and you need to do this and it's going to be an important book and blah, blah, blah. So that was really very important. And I'm grateful to the Institute and to Walter, because I think if he hadn't done that, I might have not quite started the ball rolling. Once I started rolling, then it was fun and I was hooked. Okay, so I finally came out with this book. And as I said, it is a different perspective on Einstein's life, but it's also an important perspective on 20th century culture. And the reason is that this thing, which we describe with the somewhat intimidating name of quantum mechanics or quantum theory, is actually the theory of the atom, the theory of what matter is made of. And at this point, around the turn of the century where the story began, okay, we just didn't know if human beings would be able to understand things that are a million times smaller than anything we can see. We didn't evolve, our brains did not evolve to do that, and we didn't know the rules. It clearly wasn't obeying the physics of cannonballs, etc. So it took 26 years, 2 generations of the greatest minds in physics to solve this problem. Okay, but the success unleashed the technologies of the 20th and 21st century. Okay, and let me illustrate that with the difference between old and new electronics. There are many ways to illustrate this. Okay, but this is one important one. So most of you probably know that in computers and cell phones, there are transistors, which are electronic switches, which allow you to do logic and many other things electronically. This is a transistor around 1930. It's about an inch in scale, and you made them one by one. This is a transistor in the modern era, in which you've now got it at the scale of 1,000 atoms. The same thing that was an inch is now 1,000 atoms, and you can make many billions on one chip. So that was only possible because we understood the atomic structure of matter and of the atom, so that we could build the electronics into the medium instead of having a component like this that was assembled one by one. And it was this that allowed the modern computers, cell phones, etc. Okay, so I try to really make this dramatic. So we talked about that we're hearing the movie of the Higgs boson, but this is the movie that I'm hoping is going to be made.
At the beginning of the new century, mankind faced the ultimate challenge. Science and technology ground to a standstill as the elusive atom held tightly its secrets. One man alone, the valiant Swabian, understood what was needed: revolution. This is his story.
So that's what I would like, this is an homage to Shankar, who's a big movie buff. So anyway, so that's the movie trailer. The movie, as far as I know, hasn't been made. Okay, so Einstein was born in 1879 in Ulm, Germany, to a middle-class and secular Jewish family. He was an excellent student, but he was always perceived as arrogant. And in a famous incident, he was upbraided by his Latin teacher, and Einstein protested that he had said nothing, and the Latin teacher, Dagenhart, responded, "Your mere presence here in the classroom undermines the respect of the class for me." So there was something he was doing, and he was exuding an aura, and he actually didn't like the schooling, so he dropped out unbeknownst to his parents, who had to move from Germany to Italy for economic reasons, and they were astonished to see that their son, this brilliant, promising student, had dropped out, shows up their doorstep, but he says, "Don't worry, Mom, I'm going to self-school. I'm going to teach myself enough to pass the entrance exams at one school in Zurich, the Zurich Poly, which will accept people who do not have a high school diploma." Okay. So he goes there. He's only 16 and a half. He does great on the math and physics part of the exam, but they actually expected him to know some French and history and things like that. He wasn't as good on that, so he didn't pass. But after another year of schooling, he did. He was admitted to the physics section in 1896 for people who would be teachers and possibly researchers in physics. And for the first 2 years, he's the best student in his group. He has the highest grades. He's very popular with the head of the physics section, Heinrich Weber. But he realizes after 2 years that they're not teaching him any of the theory, the most modern theory of electromagnetism, of statistical mechanics that he knows about because he's been self-schooling, and they're not teaching it to him. So he just loses interest. He stops going to class, his performance plummets, and when he does go to class, he kind of goes out of his way to piss off the professors. And this is Switzerland, right? So they're kind of uptight there. I mean, they believe in hierarchy and so on. So in the lab class, they have, like we do in modern lab classes, the students all get an instruction sheet at the beginning of the class on how to do the experiment. And Einstein would look away from it, walk over to the wastebasket and drop it in, and then go do the experiment, just to show that he didn't need any instruction. But in that class, he actually created an explosion in the lab, injured himself, and got an F. So it wasn't that he actually could prove it. He didn't actually back it up, at least in that class. Okay. Now, he met in class, there was surprisingly one student in the section who was a woman. This is very rare at the time. It was a very talented young physics student, Mileva Maric. And they fell in love and eventually married in 1902. And They were married till 1913 during a lot of his creative period. But then eventually the marriage fell apart and he had moved to Berlin. They divorced in 19. And after he graduated, because of this essentially alienating all the professors, he couldn't get an assistant's position. Heinrich Weber, who had loved him at the outset, hired 2 engineering students in preference to Einstein in order to teach physics. So for a while he had no means of support, but then he got a job, and he got a job in a way that tells you something else about his character. So even though the professors didn't like him, his fellow students loved him. They all loved him. They all raved about him, even at the time, before he was famous. Apparently, this particular friend, Grossman, who was well connected in Switzerland, told his father the first week of class that I have met this young man, Einstein, and someday he will be a very great man. So, he had this sort of dual relationship, against authority, but very supportive of his peers and liked. And as he said, even though he had these problems, he didn't get an academic position immediately. He never lost his enthusiasm. He said, I am a cheerful fellow and have no talent whatsoever for melancholic moods. And so I found this all very endearing, reading all these letters between these two, for example. And one of the things I found particularly endearing was that he would sign his letters the Valiant Swabian. So this is not, I didn't just make up that name. This is a romantic poem of the Swabian region where he was from in Germany. And this mythic crusader knight defeated the Saracens through his intelligence, etc. And Einstein would sort of sign his letters to Mileva with this, sort of like me signing my emails Indiana Jones or something. So anyway, so he's a very, very winning character, and it was very interesting to get to know. Okay, here he is as a student at ETH in 1898, around age 19. Here he is as a young father with his first son, Hans Albert, in 1904. Let me now switch more into the scientific meat of what I'm going to tell you today. So let me give you a sense of the scientific timeline of his career. In 1900, we're going to learn about Max Planck and the beginning of the quantum era. In 1905 is when he bursts on the scene, even though he's been working before that with quanta of light, special relativity, E equals mc squared. 1906-07, he does very important work, which I won't be able to talk about except a tiny bit, about quantization of energy. 1908 to 1910, he introduced the concept of wave-particle duality. 1911 to 15, he gives up on this, I'll come back to that, and goes to the general theory of relativity, the thing he's probably most famous for, which is the theory of gravity, and then goes right back to quantum theory, talking about atomic processes and randomness in 16, 17, and then this brilliant work that's not very well known on what's called quantum statistics, 24, 25. By 1926, not Einstein, but Schrödinger and Heisenberg write down the modern form of quantum mechanics, but Schrödinger had a big boost from Einstein. But Einstein then doesn't like it, and I'll tell you about that at the end of the lecture. So this is 20 years, and I would say that if all of these works were done by different people, they would be recognized with something like 7 to 10 Nobel Prizes, probably 6 to 7 in quantum theory. But anyway, so he had a very productive 20 years. So let's throw out these minor contributions and talk about the things that are really important. I'll just be able to dip into, well, this I'll talk about quite a bit, just dip into this and a little bit here at the end, and then talk about his philosophical views. Okay, so briefly, when he was just starting off at the patent office, I forgot to mention, the reason I mentioned Grossman is Grossman, through his connections, got him the famous job in the patent office. And when he moved to Bern to work in the patent office, he made friends with this group of people who were all penniless. This guy, Konrad Hibiki, was a mathematical student rather. Maurice Solavine was a philosopher, and Einstein was Einstein. Their life reminds me a little bit of the opera La Bohème. We have a little musical theme anyway. He was so interested in music. They had these meetings where they talked about the great ideas and imagined a great life ahead, sort of like the poet and the artist and the musician and so on in La Boheme. And in this case, it actually came true for one of them. Now, this guy and Einstein seem to have a very jovial relationship. Conrad named him Albert Ritter von Steisbein. Steisbein is something back here, apparently. So, and they just teased each other all the time. So, but at some point, this group, which was called the Olympia Academy, disassembled as these guys moved away, and Einstein wrote to Hibiki in 1905, and this is the only substantive letter we have from his explosion of genius at that time. So I want to tell you a little bit about this letter. Okay. So he's writing to Hibiki, his buddy who he jokes around with, and he says, "Dear Hibiki, such a solemn air of silence has descended between us that I almost feel as if I am committing a sacrilege when I break it now with some inconsequential babble. So what are you up to, you frozen whale, you smoke-dried canned piece of soul? Why haven't you sent me your dissertation? Don't you know I'm one of the only 1.5 men in the world who would even read it, you wretched man?" That's really how he wrote it. Okay. And then he says, "I promise you 4 papers in return. The first deals with radiation and the energy properties of light and is very revolutionary. The fourth study is still a mere concept, the electrodynamics of moving bodies by the use of a modification of the theory of space and time." Well, this is a pretty interesting letter, right? You know, I am doing something very revolutionary, but then I'm also modifying the theory of space and time, but this is the revolutionary thing. So, okay, so I don't know what Hibiki thought about that. These contributions all came out in this famous issue of the Annalen der Physik in 2005, and the theory editor was Max Planck, who we're going to see in a minute, was critical in the rest of the story, and he let all these crazy things through, to his eternal credit, particularly because we learned later he didn't believe they were all correct. Okay, but he loved relativity. So very revolutionary. That's what he said about the paper on the energy properties of light. And for his whole career, he always said that relativity was not revolutionary, it was evolutionary, but this was revolutionary. So what did we know about light in 1905 that would make this revolutionary? Well, this guy, James Clerk Maxwell, in the 1860s, had proposed a wave theory of light, and they would be electromagnetic waves. They're electromagnetic waves where what I'm showing here is the electric and magnetic fields. If you don't know, from college physics, then there's something. They talk about the electrical energy and the magnetic energy that's flowing. They represent that. And he showed that all these waves, no matter what the wavelength, lambda, or the frequency at which they oscillate up and down, that all these waves move at the same speed, which had been already measured to be the speed of light, about 300 kilometers per second. Okay, so as I said, if you look at the distance between two crests in the energy, it's lambda, or in the field, it's called the wavelength lambda. We are contractually obligated to use these Greek letters, so you know that we are actually a secret society with special knowledge. And the frequency is denoted often by the Greek letter nu, and they're related inversely by the speed of light. So that's sort of worth remembering. Okay, and since there was no limit to the wavelength or the frequency, Maxwell had discovered what we now call the electromagnetic spectrum, which is, as you vary the frequency, you go from radio waves in the megahertz up to gigahertz, which is mobile telephones. That's the waves that we use in cellular technology, microwaves. I'll get back to infrared in a minute. And then up here at huge frequency of hundreds of terahertz, we have light waves, and they have a short wavelength of about half a micron, half of a millionth of a meter. Now, one of the things that also came up and that Maxwell knew but became even more important in the next decades was that matter is continually emitting and absorbing this electromagnetic. Oh, and I forgot to mention, there is stuff beyond light. There's ultraviolet, which is very relevant here in Aspen. You want to avoid that. And if you go to higher stuff, you know, it's good for medical imaging, but it's very dangerous. Okay. And the photon picture, the quanta of light, explains why it's so dangerous. Okay. So, and I'm sorry, I forgot to complete this statement. So it was understood that matter is continually emitting and absorbing radiation, and that we'd like to understand that process. The exchange of energy between electromagnetic radiation, which is bathing this room, and it's not bad, it's not like the radiation from, well, if it were gamma, it would be bad, but it's not gamma. So it's bathing this room, and you're absorbing and re-emitting it all the time, and that's actually the thing that we see when we put on our night vision goggles in the dark. You're still emitting this radiation, which we can see, but it's not in the visible spectrum, it's in the infrared. And so the big question was how to describe this interaction of matter with radiation. Okay. So, and it begins again with Max Planck, who I've already introduced. Here he is in 1900 on a kind of bad hair day. And his goal was to explain the universal properties of this so-called thermal radiation. Okay. Now, so imagine, you all know actually, Aspen's a good laboratory for this. So if you're going to go on a hike, there's a reason you don't typically wear a black t-shirt. What is that reason? It really absorbs, right? So black is absorbing all the wavelengths of light, and therefore it heats up very quickly. Put on white, it reflects a lot of it, don't get as hot. So physicists invented this ideal black body that would absorb all radiation, even radiation you can't see in the infrared or in the ultraviolet. And they said, let's describe that, because that's what we always do. We look for the universal thing first. So imagine light coming in and being absorbed by this black body. Now, if this black body is on Earth, its temperature is going to be about 300 degrees in the absolute scale. And it turns out that that temperature tells us that when it re-emits the radiation, it's going to do it at infrared. I showed it at red because you can't see infrared, but it's infrared. Okay, as I said, you see that with your night vision goggles. And the critical question was how much energy is emitted as radiation for a given temperature. And we're going to describe this, as I said, you need to use your special symbols. So this is the Greek symbol rho, and it's a function of the frequency nu and the temperature T. And nu is also related to the wavelength, as I said. And this became such an important thing that Einstein said, that it would be edifying to measure the brain matter sacrificed on the altar of finding this universal function, and no end to this cruel sacrifice is in sight. So he said that in 1913. Now, I know this is the hardest part of the talk, because we have a function, and it's a function of two variables. I just want to warn you, when I teach my students about quantum, I say, this isn't rocket science. This is really hard. So it can be kind of confusing. Got a function of two variables here, okay? And just to confuse you more, I'm going to replace the variable frequency by the wavelength, because somehow that's how I got this plot off the internet. Okay, and what this shows you, so what's really telling you is how much energy at a certain wavelength is emitted. So you see the highest point here is the most energy, and that's about 10 microns of wavelength. That's infrared, we can't see it, but that's what we're all emitting, okay? And that's because our temperature is the Earth's surface. If we warm up an oven or something, or metal to red hot, the peak shifts to shorter wavelengths, and a little bit of the energy you see there is emitted where we can see it at the red part of the spectrum. But most of the energy is actually invisible to our eye in the infrared. So what is it that the eye sees? Anybody have a guess? Well, it sees, of course, the temperature of the sun's surface, right? So some of us may believe that we evolved so that we could see very well the radiation that's emitted by the sun, which is at 6,000 degrees Kelvin on its surface. So this is an example of three different curves of black body radiation where the peak energy that's being emitted changes to shorter and shorter wavelengths as you heat it up. That's this function rho of nu and t that we want to know. And this is all the critical thing in all the energy balance in terms of global warming and so on. It underlies all that stuff. And actually, if you've come to these other lectures, you probably know that the universe is actually a very cold black body. This is the measurement of the cosmic microwave background against frequency now here, which shows that the universe behaves from the energy from the Big Bang is still around in sort of the form of black body. Okay, so this was this biggest challenge of the 20th century. Planck was a great thermodynamicist, and he was trying to figure this out. And he thought he had found the black body law. So the mathematical function for this curve, and also as a function of temperature, which I'm not showing here, that is the solution that he was looking for. And he would then call that the black body or thermal radiation law. That's the terminology. That's what he was looking for. And somebody, a colleague, Wilhelm Wien, had already proposed a formula. And in 1899, Planck wrote a paper proving that Wien's formula was the right answer. And here he says the limits of the validity of this law coincide with those of the second law of thermodynamics. Now, thermodynamics is this fundamental law of heat, set of laws about heat that Einstein said will never be violated, and it has never been violated. So when Planck said in 1899 that this Wien formula followed from the laws of thermodynamics, he was saying, I'm betting my house on this, okay? This is what the right answer is. Now, they didn't have these curves to really check. They only had parts of them, right? So Planck was very committed, and he had this unfortunate situation arise. And this is actually how I decided, this is when I decided to start writing the book, when I learned about this interesting situation. So it was about 9 months later, and he had this friend who was presenting better measurements of the black body formula at the invisible wavelengths, at the infrared, which previously they didn't have, okay? This guy named Ferdinand Kurlbaum. And these are the data. Now, the confusing thing is the data are being plotted versus temperature, not versus frequency, sorry. But it's the same function, rho, okay? And this, the data are in this green straight line as a function of temperature. But the Wien law that Planck had bet his house on looked like that. It didn't agree at all with the data. And he was in the audience, the same audience that he had said that this absolutely had to be true, and he was supposed to comment. So this is a theorist's worst nightmare. It's actually my worst nightmare, because when you do these things, if there are approximations, you can get out of it. You can say, oh, I guess that approximation I used wasn't right. But if you say it's fundamentally exactly true, then you're just a bad physicist. You're a bad theorist, let's say, because you don't do experiments, so you got to be good with the theory, right? So, so this was really bad, and the question is, what is he going to do? So luckily, these buddies had told him about this impending doom, and he had started to think about it. And by the time he got there, he said, okay, I don't actually know why this is true, but I have a new formula that I've guessed, which is a little different from this one, and it goes perfectly through the data. And I won't show it, but I have that picture. It did go perfectly through. Okay? So he basically guessed the right answer in October. He says, I don't know why this is right, but at least I can tell you what the function is, I think. Okay, now I got to prove it. So he has to find a justification. It takes him 2 months of the most strenuous effort of his life, as he put it. And here's his answer, okay? I'm not writing the formula. I'm writing the thing that he had to do to get from Wien's law to the correct law, which is now called Planck's law. So he had to assume something crazy. That's what he had to do, and he was desperate. In fact, he said, what I did could only be described as an act of desperation. So, okay, so what did he do? So energy underlies everything we do in physics. The concept of, the amount of oomph in everything is the energy, right? And we have at least 2 forms of it. One form is called kinetic energy, which is the energy of a mass that's moving. And the other is potential energy, which is the energy of moving something against a force. So when I move this up against gravity, I have to put some energy in, and I can recover it by letting it go. And actually, if there weren't too much friction here, it would all be conserved. However much potential energy I put here would come back in kinetic energy, and et cetera. And then I could actually catch it, and then I'd get back the potential energy. So that's one of the key elementary ideas in physics. And you can see, and this is essentially a very nice pendulum because it's a locket that wife owns. You can see that when it goes here, it has, let's call that zero energy. Okay, that's a definition. And when it goes here, it has more energy. And when I take it out, it has more energy. And it looks like the amount of energy I can give to this locket is obviously continuous because space is continuous. So if I move it a little bit, I can always give it any amount of energy I want. That's very intuitive, right? Planck had to assume that atoms weren't like that, that you could only give it a chunk of energy, and the chunk of energy you could give it was proportional to the frequency of the light that the atom would emit, times a new constant, which is now called Planck's constant, h. So that's what he assumed. Or did he? That's what he assumed to get the answer. But then he kind of buried it. He buried the lead, as they say in journalism. Okay, he kind of said h is fundamental, but I'm not sure this law is really fundamental. Not only that, but he didn't talk about it for 5 years. He derived the answer, it fit the data, and then he didn't say anything about it for 5 years. In the book, I say it's like a family that has undergone a traumatic experience and agrees never to speak of it again, right? So no one in the physics community says anything about this crazy change, which really is totally inconsistent with all our mechanics, all our view of what energy and space and time should be like, okay? So of course, who was the person who actually did this? This guy, Einstein, in 1905. So that's the thing he said, revolutionary. So he was stimulated by Planck, and he challenges the wave paradigm for light in this paper called On a Heuristic Point of View Concerning the Production and Transformation of Light. And it's the first one of the miracle year. So he says at the beginning of the paper, it seems to me that the observations regarding blackbody radiation and the photoelectric effect can be better understood on the assumption that the energy of light is distributed discontinuously in space and that light consists of a finite number of energy quanta localized in space which move without being divided and can be absorbed or emitted only as a whole. So the reason that the atoms are only getting, changes by h nu is because each chunk of light hitting it has exactly energy h nu. It never has less energy, never has more. So that would be very consistent with Planck's idea. Although Einstein didn't immediately believe Planck was right either, and in the book I go into all those nuances, which I'm skipping over. Okay, so he's basically saying light can act like a particle, not a wave. And this clearly connects to Planck's idea. The second thing he does right at the beginning of the paper, after this this revolutionary introduction, is he says, look, if you take classical physics seriously, and I explain this in the book, I won't try to go into it, something terrible happens. All the energy is sucked out of matter and it goes into radiation. This is called the ultraviolet catastrophe, because it's all the very short wavelength ultraviolet frequencies that take up all the energy, and literally the Earth would freeze. I call that chapter frozen vibrations. So he says, obviously that means classical physics is fundamentally wrong. And he was by far the first person to say this. Okay. All right. So, but there was this other obvious problem with the idea of particles of light. Okay. So we knew that light was a wave, and how do we know light was a wave? Well, the characteristic of waves is that they are disturbances in a medium. This is a animation of a water tank where there are two little posts that are bouncing up and down, creating waves. You can sort of see them there. Sorry. And what you see is there are places where the water is very smooth, where a crest and a trough from the two different sources are canceling. Other places where there are big crests. This didn't come through so well, but I think you can sort of see it. And that's where they constructively interfere, with two crests coincide. So that kind of pattern of wave interference is characteristic of waves in a medium. So did light interfere with itself like water waves? What was the medium for light? Well, we invented a medium called ether for it to go in. And the controversy raged in the first half of the 19th century. And one of the things that resolved it was the spot of Arago. Okay, so this guy, Augustin Fresnel, was responding to a competition of the French Academy of Sciences to explain the properties of light. And he submitted a wave theory of light. Mathematically, it was a wave theory. And this famous mathematician was on the jury that was picking the prize winner. His name was Poisson. And he derived a contradiction. He said, I'm going to show how crazy this is by proving something that can't possibly be true from your equations. So what he proved is that in the shadow of a circular object, right at the center of the shadow should be a bright spot. Okay, so you would think that would be called the spot of Poisson, but it isn't for a certain reason, okay, because Fresnel had a friend. Okay, Monsieur François Arago, and he's the most interesting physicist alive because not only did he do this experiment and find the spot, which is now called the spot of Arago, so even though Poisson thought it was ridiculous, it turns out if you do it carefully, it's there. But also he later became the prime minister of France and freed all the slaves in the colonies and also was a war hero and so on. So he's the most interesting physicist alive. Okay. So interference of light after this in the early part of the 19th century became routine, and people did double slit experiments and saw the bands of light and dark and so on. So that proved that light was a wave, and we had to invent a medium called the ether for it. Okay, and then, by 1890, Hertz had proven, confirmed this experimentally, and Marconi and others had invented radio. And there was this disruptive technology that was revolutionizing the economy of radio. And still there, right, Will? And nothing was more certain in physics in 1905 than that electromagnetic stuff must be in the form of waves. So was there anything that seemed to contradict this picture? Well, yes, there was. There was one obscure thing that Einstein had noticed, and it's called the photoelectric effect. So what's the photoelectric effect? So you imagine you have an arc lamp, bright source of light, white light with many different colors mixed. You put it through a prism, which separates out the different wavelengths or colors, and then you have a movable slit so you can have only violet or ultraviolet light come through or red light. And then you have the light that comes through hit a thin metal foil, which happens to have electrons that are free enough that when the light hits it, it comes off. You can collect the electrons, that's what the little balls are, and you measure the current in the circuit that you've generated. So you can tell you've created a photoelectric current, and you can measure how big it is. And the surprising thing that was noticed is that if you put through the red light, you didn't get any current, even if you made the light more and more bright. So the idea was the brighter the light is, that should be the energy in the brighter lamp. You know this from the watts on your light bulb, means more energy coming out. Okay, so why, when you make it brighter, can't the red light knock out some electrons? Okay, that was the puzzle. Okay, so Einstein came along with an answer. He said, well, okay, maybe this picture of a light wave knocking out an electron is just not fully correct. I'm going to insist that somehow I can think of these light waves as instead little trains of particles, photons, he didn't call them that, quanta of light, which each has energy h nu. And this electron is bound here by some atomic forces. So when the red light goes in and interacts and gets absorbed, it doesn't have as much energy because its frequency is lower than the violet, ultraviolet or violet light. So when it's absorbed, it just sort of jiggles the electron out, around, but it doesn't knock it out. Whereas when an ultraviolet photon comes in, it's enough to knock it. So that would explain this observation, which had no other explanation at the time. The problem is there were also no good experimental tests to prove this definitively, and it took 10 years to get them. And no significant theorist believed Einstein was right for that entire time, the next 11 years. In fact, in 1913, that's when Einstein left Switzerland, and he was attracted by this guy, Walter Nernst, who was a very pompous, interesting character who I talk about in the book. The chapter is called The Importance of Being Nernst. And Max Planck, now with a no-hair day, because this is much later. And what they did was they attracted him by saying, you're going to be able to work, you won't have to teach at all, you'll be a member of the August Prussian Academy of Sciences, you'll be the youngest member ever by 15 years. And they wrote a flowery letter to nominate him, saying he was the next Galileo. And what they did was they had to be honest, they had to apologize for his one major error, that he, Einstein, may sometimes have missed the target of his speculations, as, for example, in his hypothesis of light quanta, cannot really be held against him because everything else is so great. Okay. Well, what about the photoelectric effect? So this is 8 years later, so obviously nobody's accepted this for 8 years. So this famous American experimental physicist, Robert Millikan, really did this experiment carefully. So now I'm adding a little piece to the picture. There's this other thing that I didn't mention. There's a grid here, a metal grid, and you can charge up this grid. So when the light comes through, if you charge it up negative, since the electrons are negative, they get pushed back into the metal. So basically, you can stop the photocurrent by charging up this grid, and you can measure how much voltage it takes to stop that photocurrent. And by Einstein's theory, there was a simple equation that said the voltage you needed would be given, oops, this is really dying, but well, the voltage, called the stopping voltage, would just be a straight line proportional to the frequency of the incoming light with a slope equal to Planck's constant. That's a very specific testable hypothesis. And finally, it was tested. So here's your straight line. Here is actually Einstein's equation for how it should behave, showing the slope should be h, Planck's constant. And when you work out the numbers from the experiment, the slope is exactly Planck's constant. Those of you in the audience who are not physicists should not recognize this number, but I swear it's very close to Planck's constant. Okay, so that's a fantastic thing. And sorry, I didn't want to skip ahead there. And Millikan said this funny thing. He said, I spent 10 years of my life testing that 1905 equation of Einstein, and contrary to all my expectations, I was compelled to assert its unambiguous experimental verification in spite of its unreasonableness, since it seemed to violate everything we knew about the interference of light. So he was trying to disprove it. Well, finally, in a sort of interesting development, when they finally gave Einstein the Nobel Prize in 1922, it was for his services to theoretical physics, especially for the discovery of the law of the photoelectric. So that sounds like a great vindication, except they don't say anything about quanta of light, which is the whole justification for it. They were still scared that that was wrong, but since this was, proven experimentally, they had to give him the prize for something. And that's a story I go through in the book. Okay, so what was Einstein doing? He was entertaining the contradiction, okay? He was able to imagine that light was both a particle and a wave. And in 1909, in a work that I won't try to go through, he actually proves something to this effect, which then he goes public and he says, the next stage of theoretical physics will bring us a theory of light, which can be a fusion of both wave and particles. And those of you who know some of the buzzwords of quantum mechanics will know that that underlies the modern theory, that both the things we thought were particles are waves and vice versa. Okay. He actually fails to make this theory at the time, and then he goes off and he does this thing with curved space and light being bent, and people seem to like it a lot. They said it was the highest achievement of human thought and greatest scientific discovery ever and stuff like that, and even he thought it was pretty good. My boldest dreams have come true. But then he gets back to the real stuff, the quantum problems. Okay, so I'm in the home stretch here. So, okay. So in 1916, this is after Bohr has represented the atom by this little solar system with quantized energy levels. And he returns to this emission of light, black body radiation. He says, imagine that I have an electron in a higher energy level. It's going to give up its energy, fall down, and emit a photon or quantum of light. And this can happen without any cause. We call this spontaneous emission. It can also happen if you drive the atom with an electric field, et cetera, and the atom can do the other thing and absorb light and jump up. And what he showed was that if you balance these processes in the Bohr atom, you get exactly Planck's law with no additional assumptions. And he's so excited, he writes to his friend Michel Besso, the light quanta are as good as established. He thinks this is the greatest thing he's done in a year. General relativity was easy. So, okay, but what he has done to get this answer is he has introduced random events, uncaused events. Nothing causes this thing to drop. It just does it, okay? And that's a new thing in physics that he introduced. And he says in the paper, the weakness of the theory lies in the fact that it leaves the time and direction of the elementary processes to chance. And then he keeps stewing on it. He writes to his friend in 1920, this business about causality, to, Itzhak Perlman or, I mean, this is the most famous, Einstein's most famous person in the world probably at that point. And he's getting, or one of the most famous. So he's getting all this mail. What are the chances that he would actually read this? Well, he does read it. He decides it's okay. And the paper is another attempt to derive Planck's law. And the reason that this guy is still trying to do it is because the thing that never worked was to say, well, let's assume that we have a gas of photons, of quanta of light. You should be able to use accepted principles of thermodynamics to figure out Planck's law, but you never get the right answer. You actually get Wien's answer. So nobody had figured that out, and Bose actually had figured a way to do it. Okay, and so Einstein translates the paper, it's published, and he says at the end of it, in my opinion, Bose's derivation of the Planck formula signifies an important advance. And he recognized a buried insight by this unknown Indian physicist, which we now call the indistinguishability of quantum particles. It's not very well known, and that's why I spend time on it in the book, because it's really cool. Okay, so I'm going to spend 2 minutes on it here. So what you're doing when you derive this formula is you have to use statistical principles, because you don't know where all the quanta of light are or all the particles are. So imagine I do have 2 coins, heads and tails, and if I flip these coins, okay, what is the chance I'm going to get 1 heads and 1 50%. What's the chance of getting heads and heads? Only a quarter, right? So it's twice as likely that I get heads and tails. Why is that? Because there are 2 ways to get heads and tails. This guy can be heads and this guy can be tails, or vice versa. So there are 2 ways, and there are 4 total ways. So 2 out of 4 is a half. That's not the way quantum statistics. Nobody could believe that. So in quantum statistics, there is no difference between heads, tails, and tails, heads. Somehow nature doesn't distinguish it when we're talking about the analog for atoms. And that's what Bose had said, but he didn't really say it. Einstein said it. And Bose didn't necessarily realize he had said it. And I explained this carefully in the book. Okay, so it's a fascinating thing because it has huge implications. Okay? Einstein then discovered that if this statistical description that I just described to you really works for a gas of atoms, not of quanta of light, of photons, then there would be a new phenomenon called condensation, quantum condensation, which is actually often called Bose condensation, which is kind of ironic because Bose didn't invent it, didn't discover it, Einstein did. But it was based on Bose's statistics. And this concept underlies superconductivity, which is in all your MRI magnets and so on, and has led to about 6 Nobel Prizes. So that was his last great contribution to quantum theory. And what happened to Bose? Well, Einstein wrote a letter to his university in India praising him. He immediately was awarded a fellowship to study in Europe. And he finally meets Einstein in Berlin in 1925. And Einstein says, look, there's this new quantum theory evolving. Why don't you do this problem? But it's too hard for him. Can't do it. He gives up, goes back to India. He's revered. He becomes a great leader. But he makes no further significant contributions to physics. In fact, he says of himself, he was a very modest man, I was not really in science anymore. I was like a comet which came once and never returned again. But the epilogue is that now all of the force-carrying particles in modern physics are named bosons in his recognition. So he did pretty well with his one breakthrough. Okay, now here's the thing I love. This is like one of my favorite moments in the book. Okay, in 1925, after Einstein publishes his paper on Bose condensation, what's called Bose condensation now, this lesser-known physicist, Schrödinger, writes to him, says, you made a mistake in your paper. And Einstein says, no, I haven't made a mistake, although you are justified in your reproach, because it's so weird what he's saying, okay? And then he writes a little diagram to explain to Schrödinger how the statistics should work. And you see, it's really the 2 coins. So here's heads, heads, tails, tails, heads, tails, tails, heads. That's the coins. And these are the quantum coins. And heads and tails, there's only one of them. So he explains it just the way I explained it to you, to Schrödinger, who then goes off and invents quantum mechanics. So I love this. Okay, so in the next year, with a lot of interaction with Einstein, Schrödinger invents one form of quantum theory, Heisenberg, an equivalent form. And Schrödinger actually thanks Einstein. He says, I owe my theory to brief but infinitely far-seeing remarks by Einstein. Okay, but then when the theory has been sort of played around with for about a year, Einstein writes to his friend Max Born and he says the following thing. He says, quantum mechanics is very impressive, but an inner voice tells me it's not yet the true Jacob, the real thing. The theory produces a good deal, but hardly brings us closer to the secrets of the old one. Now, the old one is sometimes translated as God, but to him, it's just sort of the nature, the truth, okay? I am at all events convinced that he does not play dice. So that's the God does not play dice, but actually, as you'll hopefully find out in the book, it's a lot more subtle than that. So he just makes this decision after 1 year that all the stuff that he's helped build and really been critical in building, he's not going to use it. He doesn't use it. 30 more years of his career, 25 more years, doesn't use quantum theory. And he says, near the end of his life, all the 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quantum? Of course, today every rascal thinks he knows the answer, but he is deluding himself. Okay, that's Einstein for you. Okay, so now to wrap up, let's talk about just briefly about the nature of Einstein's gene. So from reading all these papers and letters, I think he is the paradigm of a deep thinker. He's not a mathematical genius in the sense that Isaac Newton was, but he's a conceptual genius, probably the greatest one in the history of science in terms of understanding deep. We've seen that he's a flexible thinker, can think that things could be waves and particles, even though they seem to be contradictory, but he's also an insightful critic of classical physics. And he has this talent for unification and simplification, which came out to a large extent in his work on relativity. What was he like personally? Well, he was very charismatic, as I've said. He had a great sense of humor. He was adored by his friends. He was a great lover of music, and he was very attractive to the opposite sex. An acquaintance said this of him at age 43, "The strongest impression is one of stunning youthfulness, very romantic and reminiscent of the young Beethoven. And then laughter erupts and one is faced with a student." And here's a nice picture of that. So here's Einstein in 1913 playing at a outdoor fair in Zurich and developing a connection with the attractive young violinist across from him. So this is a very rare photograph. I've never seen it anywhere else. I found it. Another thing that I haven't talked about is he was an early proponent of secular humanism and of the universal rights of man, and that was a very important part of what he did in the later part of his life. And the last thing is that science was his existential philosophy. So, get the quote correctly. In his autobiographical notes, he says, "As a young man, I rejected the nothingness of the hopes and strivings which chase most men restlessly through their lives. In this way, one could satisfy the stomach, but not the needs of a thinking and feeling being. Instead, he would devote his life to understanding the huge world which stands before us like an eternal riddle. The contemplation of this world beckons us like a liberation." And so he said that physics is an attempt to grasp reality as it is, independently of it being observed. And that was his problem with quantum theory. Quantum theory breaks down the barrier between the physical phenomena and the observer in a way that is very puzzling. I still think it's a wonderful objective theory. We could talk another hour about that, but it does break down that barrier much more than classical physics. And therefore, to Einstein, it seemed to undermine the objectivity of the theory, the eternal truth of the theory, and he used to tweak other physicists by saying to them, "Do you really believe the moon isn't there? Is only there when I look at it." So, okay. So in a beautiful tribute to his mentor, Max Planck, or his friend and mentor, Max Planck, he wrote, "I believe that one of the strongest motives that leads men to art and science is escape from everyday life. A finely tempered nature longs to escape from the personal life into the world of objective perception and thought." So in keeping with the analogy to the young Beethoven and the musical love, I could make an analogy of Einstein's relation to quantum mechanics between that and Beethoven's Ninth Symphony, where you have three movements that are orchestral instrumental movements of incredible beauty, and then in the middle of the fourth movement, the instruments are interrupted by the baritone singing, "Oh friends, nicht diese Töne," not these tones, not this music. We're going to find a different harmony to finish this thing. And Einstein was trying to find a different harmony to finish the quantum theory that he had started, and he never found it. Thank you for your attention.
So here's what we're going to do. Doug, you take the question from your audience, and when you're finished, because you have to go out and sign the books for people who want to buy it, you tell them time is up, okay?
Okay.
And please repeat any questions for the audience.
Okay. I'm still mic'd, so I can do that. Yeah, so